In this section, we will learn about the concavity of a function. Concavity says how a graph of the function bends, and it bends in two ways. One is concave up, another is concave down. If you have a container, if it holds water, suppose you have a container and it can hold water when its mouth is upward, that shape is called concave up. And when it spills water, when water falls from the container, that shape is called concave down. So this is, we may say, this holds water, and this spills water. So a graph of the function has two ways in which it bends. One is concave up, another is concave down. Now let's see some of the graphs. Suppose we have the graph of y equals to x square. Y equals to x square is a parabola which looks like this one. Clearly this is concave up, and it is concave up throughout all the region. It is concave up for all x. And if you have, let's say, y equals to minus x square, then its graph is in this way. So this is concave down for all x. This is concave down, and this is concave up. Sometimes a graph is the mix of both. Suppose we have the graph of y equals to sin x. Let's say y equals to sin x, and its graph looks like this one. This is 0, this is pi, this is 2 pi, x axis, y axis, and this is minus pi, minus 2 pi. So in this region, from 0 to pi, our graph is concave down. It spills water. From pi to 2 pi, it is concave up. It bends upward. Also, you have y equals to x cube. In this way, y equals to x cube. This is the graph of y equals to x cube, where here it is concave up, bowl is upward, bending is upward, so it is concave up, and here it is concave down. Region when x is between 0 to infinity, it is concave up, and from minus infinity to 0, it is concave down. And there is also another term called inflection point. Inflection point is the joining point where the both region joints, both bending joints. So here this point is called inflection point. Inflection point. Here concavity changes. Either it will change from concave down to concave up, or like this one. Here also you have concave down and concave up, and here this is also inflection point. Here you have concave up, then it's concave down. The point where concavity changes from concave down to concave up, or concave up to concave down, is called inflection point. In mathematically, where concave up, at each point our tangents are below the curve. Here the tangent is this one, here the tangent is this one, here the tangent is this one. So at each point, the curve and tangent lies below the curve, and concave down, tangent lies above the curve. At each point, the tangents are above the curve. So here tangents are below the curve. Here tangents are above. Tangents are above the curve. When tangents are below the curve, the derivative of f is increasing, and when the tangents are above the curve, we say derivative of the curve is decreasing. When derivative is increasing, f dash is increasing. What about double dash? Double dash is positive. And when derivative is decreasing, its derivative f double dash is less than 0. So we can use the derivatives to find in which region our graph is concave up or concave down. If we are dealing with double derivative, if in some region double derivative is always positive, then that region is concave up. And if in some region its derivative, double derivative, is negative, then that is concave down. Suppose first we have the function fx equals to x square minus 8x plus 3. Our goal is to find the region where function is concave up, concave down, and what are its inflection points. First we will find double derivative. So to find double derivative, we have to compute its first derivative. What is the derivative of this one? Derivative of this one is individual derivatives. The derivative of x square is 2x, derivative of minus 8x is 8, and derivative of 3 is 0. So second derivative is the derivative of first derivative. What is its derivative? Derivative of 2x is 2, and derivative of 8 is 0, 0. So this is our double derivative, f double dash of x. Note, this is always positive because f double dash x is a constant and which is a positive number. For any x, we have always 2. So f is concave of in minus infinity to infinity. In all x, our function is concave of. Now we have our function is x cube minus 3x plus 2. We have the same question. We have to find concave up, concave down, and the inflection points. First, we will find its first derivative. Derivative of x cube is 3x square. Derivative minus 3x 3, and derivative of 2 is 0. Then double derivative of this one, 3x square, derivative 6x, 2 is power 3 times 2, then x to the power 2 minus 1, which is 6x. See, this is not always positive. So we have to note where the function, where the double derivative is positive and where it is negative. Now we'll make a sign chart. Here we'll make our real number line, and we'll find the point where f double dash x is 0. Here our double dash x is 6x, and it becomes 0 at x equals to 0. So at 0, our double derivative is 0. We will plot that point. So we have 0 here, and this point divides our real number line in 2 parts, and from each part we'll pick one point and we'll check the sign of f double dash. Suppose here we have point 1. What is f double dash 1? It is 6 times 1, which is 6, which is always positive. And if at one point double dash is has some sign, then the whole part has the same sign. So f double dash is positive in this region. So f double dash is, so f is concave off in 0 to infinity. And here let's pick, here we have minus 1. What is f double dash minus 1? It is minus 6, which is less than 0. So at one point it is negative, means at all points it is negative. So what we have, therefore f is concave down. Here negative means concave down, and this interval starts from minus infinity up to 0, open interval. F is concave up in 0 to infinity. This part we have double derivative positive, and at this point our concavity changes from concave down to concave up. So at 0 is our x component. What is y component? At what y? We will put the 0 in place of f. So we have f of 0 is 2. So at 0, 2, f has an inflection point. Let's do another example. Suppose we have our f 2x to the power 4 minus 8x plus 7. What is this double derivative? First derivative is 4 times 2, 8, x to the power 4 minus 1, 3 minus 8. So double derivative 3 times 8 is 24, x to the power 3 minus 1, x square. So this is our double derivative. Now we will find where our double derivative is 0. This is 0 implies 24x square is 0. That implies x to the power 2 is 0. That implies x is 0. So we have only one point where double derivative is 0. Next sign chart, we'll plot the point 0. In minus infinity to 0, in this part let us pick minus 1, or let's pick minus 2. So f double dash of minus 2, 24 times minus 2 square, which is 4. 24 times 4 is 96. So f double dash is positive. So at all the points f double dash is positive. In this part also f double dash is positive, because take any point, the square is positive. So here we have positive throughout. So therefore, or in minus infinity to infinity, f is concave off. So at all points our function is concave off, our double derivative is positive. And is this a point of inflection? The answer is no, because here we have concave off, here it is also concave off. So this is not a point where concavity changes. So there is no inflection point, no inflection point.